of such a function with two variables. Let's start with 11 on 531. We're given f of x comma y, and this is the square root of y minus 3x. At this point, there is only one condition I have to state. Can anyone tell us, remind us, and I'll sip some water. Can anyone tell us what we need to write? Anyone? Is anyone listening to me? Anyone?
Is it something where we write 1 over
Y minus 3x has to be greater than or is equal to 0 because the square root can only be taken from positive numbers or 0. This is the only condition. So I will say the domain of this function is any ordered pair such that this is such that, or having the property. One or the other, whatever you want to consider it, that y minus 3x is greater than or equal to 0. There is nothing else. You can also write the condition as y greater than or equal to 3x. It doesn't matter, one or the other. Let's also look at number 14 on the same page. So we have, I think it's k of x comma y equals 1 over x plus y over x minus 1. Any conditions that come to mind here? What do you think? Anything? What do you think? Any restrictions that I have to write? Anyone? Well, x cannot be 0 and x cannot be 1. There is no restriction for y. Y is in the numerator. So then the domain of this function, again, is made out of any ordered pair such that x is not 0 or not 1. Y can be anything. There are no restrictions on y. Any questions? Let's look at one more. And then let's look at a word problem to see how this works and why two variables. Well, let's say number 10. We have g of x comma y is natural log of x squared minus y. Can anyone give us anything? Can anyone tell us anything about this? Any restrictions that you can think of? Well, the same condition here. These two functions are quite similar, but this one can have 0, but this one cannot. So x squared minus y has to be strictly greater than 0. You can move y and say that this is y is less than x squared, or you can leave it as is. It doesn't really matter. So the domain is then any ordered pair such that having the property that y is less than or equal to x squared. Less than, not equal to. And that's the domain of this function. Let's look at a word problem now. Let's say savings and interest. 18 on page 532. So we're given the formula A of R and T. And this is 1,000, 1 plus R divided by 12, and the power is 12t. This function is a function of two variables. R, which is the annual interest rate, and T is time in years. So the fact that we have 12 here, it means that the interest is compounded every month, 12 times a year. Okay, A is the accumulated value, and 1,000 is the principal, what we deposit today. In part A, we're asked to determine A of 0.05, comma 10. What does this mean? It means when the annual interest rate is 5%, and we're calculating the accumulated value when time after 10 years, when T is 10. All we have to do is just plug it in, as we just did. 1 plus 0.05 divided by 12, and since it's 10, it's 120. I cannot do this by hand. Let's put it in the calculator. 1,000, don't forget the parenthesis, 1 plus 0.05 divided by 12, close the parenthesis, put the caret. It's only one number. Okay, I'm not going to put parentheses. So it's 1,647.01. In part B, we're asked to determine what is the interest earned. So the interest earned is 1,647.01 minus $1,000 that we put in. So it's 647.1. How much more interest can be earned over the same term, 10 years, if the APR, the annual percentage rate, is increased to 5.75? Okay, no problem. So A of 0.0575 and 10. All I have to do is just plug in the same thing. 1 plus 0.0575 divided by 12, and the power is still 120. So I'll simply go back and recalculate everything. I'm just going to insert 75 and press enter. So the answer is 1774.69, and the question was asking us how much more interest can be earned. So it's the difference. So 774.69, and I subtract 647.01, and the extra is 127.68. So the extra, if the interest rate goes up a little bit, extra interest, 127.68. Any questions? And that's how it works. Every time we have a function of two variables, in order to evaluate, we have to be given both numbers to plug it in. Okay, now let's talk about most important part, and 6.3 actually, both of them, partial derivatives. So a function like this that I just made up, or just let me copy one so we work on an example directly. Page 539. Let's start with I don't want to jump into exponentials and logs just right away. I just want to take it easy. Let's say f of x comma y equals 2x cubed plus 3xy minus x. So this is problem 4. A function like this, when we want to differentiate it, we can't. differentiated as we did with functions of one variable. We can only determine derivatives for this as long as we keep either variables constant. The notation now, it's not going to be dy over dx or df over dx as we had it in the past. No, because it's a function of two variables. So if I want to determine, I can determine four different derivatives. I can determine fx, which means y is kept fixed. I can determine fy, which means x is kept fixed. I can determine fxx, which means the second derivative, I differentiate the first one with respect to x and then again with respect to x. I can determine f of xy or f of yx, which will be the same. So, and f of yy. So you can say, but you said 4. Well, there are 5. Yes, but these will be the same. So I can differentiate with respect to x one time, keeping y fixed. I can differentiate with respect to y one time, first derivative, keeping x fixed. I can determine the second derivative, differentiating this again with respect to x. I can determine the second derivative, differentiating this again with respect to y. Or I can differentiate this with respect to x and then with respect to y. So this is one notation. Here is the other notation. This is fx. The partial derivative of function f with respect to x, keeping everything else fixed, like the y fixed. Okay, here's another. Let's say for these. So in order to determine, this is going to be d2f over dx2. But not the straight d, but the round d, to signify that we are talking about functions of multiple variables, and this is the partial derivative. So this is called partial derivative. This is the second, so this is the first partial derivative. This is the second partial derivative with respect to x. Okay, so let's practice this with this function, and then we'll choose more sophisticated functions in a minute. So let's say we want to determine, oh, that's not good. Let's say we want to determine fx. I think it's done. That means I differentiate function f with respect to x. Automatically, I will keep y fixed. So the first piece is clear. This will be 6x to the second power. Here, this is fixed and this is fixed. So when I differentiate 3y, that is just a number, times x, I get just positive 3y. When I differentiate negative x, I get negative 1. Any questions? Now let's say we want to determine fy, which is the partial derivative of f with respect to y. Okay, back to the original problem. This is fixed. So when I differentiate it, I get 0. These two are fixed. So when I differentiate this, a number times y prime is just that number. This is fixed. When I differentiate a number, it's 0. I get 0. Any questions? Now let's suppose we want to determine the second derivative with respect to x. I go back to the first derivative. I differentiate the first term and I get 12x. But this is fixed and this is fixed. These are numbers. So when I differentiate, I get 0. So that's it. Now let's differentiate fyy. So this is fy differentiated with respect to y. I don't have anything. Finally, I want to differentiate the first derivative with respect to y. Okay, when I differentiate the first derivative fx with respect to y, this is 0, this is 0, this is 3. If I want to determine fyx, I differentiate this with respect to x. I have to get the same thing, and I did. This is how we determine partial derivatives. What does that mean? The rate of change of a function when one variable is fixed. The rate of change of function f when y is fixed is this. The rate of change of function f with respect to y when x is fixed is this. Okay, so now we can look at other functions, maybe slightly more sophisticated. They're also called first order and second order partial derivatives. So maybe I should mention that. First order partial derivatives. They are fx, fy, depending on the variable, of course, we can have other variables. And second order partial derivatives, fxx, fyy, fxy, fyx. Okay, so I'm looking on page 540, and I'd like to choose, if you would like to choose from there, that's fine. And do the same thing with slightly more sophisticated functions. Or back to page 539, if you want to pick from there, or I will. Okay, well, I am going to pick 31. So f x comma y is x to the 5th, y to the 4th, plus x to the 3rd, y squared. We're asked to determine all 4 second order partial derivatives. fxx, fyy, fxy, fyx. And then move on to something else. I cannot determine fxx, fyy, fxy, and fyx before I determine fx and fy. Like before, we couldn't determine the second derivatives